Hello, thank you all for being here. Today I want to talk about another mechanism to create an entanglement between physically separated qubits. And what I mean by that is that we actually want to create a state between two qubits which they are not in close proximity to each other. And there has been a lot of theory on how to achieve this sort of states, more deterministic protocol as well as some experiments, more probabilistic protocols as well as, again, more experiments, and yes, again, more theory protocols as well as some quite recent results from yesterday. I hope you did not miss it. And however, I want to present a completely alternative mechanism to generate this sort of states. And for that, I want to go back into a really simple system in which I just consider just two qubits. They are coupled to a 1D waveguide, a transmission line, you name it. And I ask myself, what happens if this environment is hot? So you have let's say a thermal environment, and I couple just two qubits into it. Can I actually extract some quantum correlation, some entanglement out of it? And of course, the answer is no. Two qubits in a thermal reservoir will just thermalize, so nothing can actually be done. But now let me actually introduce our setup, which is somewhat really similar. And instead of having just a waveguide, we actually just, so we now just have a cavity, a filter, a resonator, something that is actually coupling our waveguide to a hot reservoir. So you can imagine here we have actually two systems, one cold reservoir in which I just have the, let's say the waveguide and the two qubits, and one hot reservoir which is coupled through the waveguide to the cold reservoir. And of course I do quantum optics, therefore I can solve it using a master equation approach. And I will not go into the details, just for completeness. What I have is just some thermal cavities, a two-sided cavity, so I have two jump operators. I have a qubit system, just the tuning, they just decay into the waveguide, completely independent system. And there is one subtlety, and is that I consider my waveguide to be unidirectional. So basically, this is just some odd coupling term, but this is what appears when you actually derive a system in which all the propagations or all the excitations go from, let's say, from the left to the right. So in this case, we are assuming that all the photons emitting from the cavity, they just go into the qubits, but there is never back action. This small caveat is actually not really necessary. I can really consider a more experimentally friendly setup where I have a bidirectional waveguide. If I impose some opposite but equal detuning on the qubits, but in terms of mathematics, it's actually a bit more easy to consider this unidirectional setup. So this is what I will stick to. So now that I have this setup, I'm wondering if I now look at the state, like the steady state of the two qubits after getting long enough, how they look like now that I have actually these two new parameters. And here I want to quantify the entanglement between the two qubits using the concurrence. This is just let's say an entanglement measurement, which basically is 0 for a separable state to 1 for a completely bell state. Anything in between just quantify some finite amount of entanglement. We actually find quite a bit of surprising result in which if the bandwidth of the cavity is pretty large, so it basically means that the thermal reservoir just couples to the cavity in a way, let's say, fast, and then it emits the photo also fast. We somewhat recover the case where the two qubits are in a thermal state, so nothing happens. We call it as the Markovian regime. On the other hand, when we gradually decrease the bandwidth of the resonator, so we are approaching a regime which we'll call it non-Markovian, we actually observe the emergence of quantum correlations or entanglement between the two qubits, which surprisingly also grows as we increase the thermal occupation or the strength of the fluctuations. So this was just some numerical findings. I will now just try to dedicate the rest of the talk trying to illustrate what's going on, trying to get a bit the physics behind it. And for that, I need to open a parenthesis, and I have to consider a completely different system. For those in the community, maybe it's well known. But if I now consider the two qubits in a waveguide, which are driven not by a thermal state, but by a coherent state, it has been shown more than 10 years ago that there is an interference effect due to coherent and incoherent processes in which the two qubits actually become highly entangled. It's a pure state, and as you increase the coherent driving, it actually projects into the singlet state, which is one of the Bell states I introduced before. This is just not just a theory proposal. It has been done experimentally quite recently, so it's actually quite relevant in the field. But here I would like to emphasize that we have two qubits given by a coherent state. And I would like to emphasize that a coherent, so the phase space representation of a coherent state, this is just a parenthesis. I will make a bit more sense later on. It's just a dot in phase space, which is well defined. So now let me close the parenthesis and try to make you understand why was this important. So my original problem, I have one bosonic degree of freedom. I have two qubits. We can map it using the P representation of the bosonic field into a stochastic master equation. So what we do is we now have a stochastic description of the two qubits, which are being driven by some classical stochastic field. So basically what we are doing is we can transform our problem, and this is an exact mapping thanks to the cascaded interaction. We can transform this into basically two qubits in a completely thermal reservoir. And if we want to recover the physics or the dynamics of the original system, we have to average over all the ensemble. In this case, it's just going to be over some thermal distribution given by the Orsen-Ullmann process. So now you can already see the relation to the parenthesis I opened before, because now we don't have a coherent driving anymore. We actually have a fluctuating driving. And in the Markovian regime, where the dynamics of the source is really, really fast, what we actually see that the phase space representation of the thermal cavity is just a mess. Just some randomized phase and amplitude, so there's no coherence at all. And then it kind of makes sense that the qubits are thermalizing and there is no room for any coherence. However, the old regime, where kappa is really small, the dynamics of the thermal cavity of the filter becomes lower. And you can see now that this somewhat already resembles a coherent state so the phase space of a coherent state. And actually, if we now go to the limit where it is really a static fluctuating field, we can actually solve it. And it's really now analogous to the coherent state. But this would be the coherent state between the two qubits for a single trajectory. We still need to average over the whole ensemble, as I said before. And this is one of the main results of this part, in which we actually see that even averaging over the whole thermal distribution, entanglement is not totally destroyed. Entanglement persists, and we actually see that if we here define this phi quantity to indicate somewhat the flux, which is basically being output of the cavity, or this is the number of photons per unit of time the qubits are seeing, and we actually see that if we increase this flux, the qubits are actually converging into a highly entangled state or into the singlet state. But this system was quite idealized, so we just take this to be zero. I don't have time actually to go into the details, but we are able to work out the whole theory behind it, and even going beyond the quasi-static limit. And what we actually found out is that entanglement is always bounded. So you can, in realistic systems, when you increase the flux variable, you will always reach a plateau, and this being a dome. And the reason is because as we increase let's say the thermal fluctuation, the strength of the path, we start to populate other. So basically, the population of the other states start to grow, and this turns out to be quite detrimental for the entanglement. Still, in our work, we are able to find some effective model in which we actually can predict the critical value in which the entanglement peaks and starts to decrease. And I would like now to introduce some theoretical proposal from the Walter-Meister Institute, in which we would like to basically just bring this into the experiment. And here I will just put some numbers, which are the one we are usually working on. You can see that we actually require some high Q resonators, but this is not really a problem from a group in which you can even achieve a quality factor of 1 billion. And this is actually to show that we can even achieve entanglement with a source at room temperature. And with that, I would like to finish by saying that, so basically I presented a novel mechanism to create entanglement between physically separated qubits. I did not have time to go into so we had other implementations, specifically for a phononic waveguide. And I would like to emphasize that this is a completely autonomous protocol. It really requires no control whatsoever. You just have to turn on the heater, go for a coffee, come back, and you will have entanglement. So thank you.